I'm audible, back, all good? Yeah, thank you for the nice introduction. I'm Soubhik, that's my Twitter handle. Uh, I'm not super active, but if you have any feedback, do drop me a message. I'm from Intuit. I'm a noisemaker by day and a coder by night. So here I am to make some noise for you. So today, my talk is about a few stories. And these stories are about, the way stories are, like it starts with a problem and then, there is a beautiful resiliency pattern that comes and, solves that problem. But then in the end, there is some twist as well. We did learn a few lessons, not like textbook type of things, but, few unusual lessons. And I'll be taking you through that journey. Hopefully you enjoy it and, it turns out helpful to you as well. So, a little bit of a context. So, Intuit is a financial software company. We make products for accounting, for tax, and personal finance, and payroll and stuff like that. So, most of our products they do things that we don't like to do. Like we don't wake up in the morning. Hey, today is the day I am going to file my income tax. Wow, no. Most of us don't do that. And what that means is that we tend to delay things to the point where the deadline is just around the corner. And this means that there are days right before those deadlines where our traffic surges. We see huge surges of traffic. We're talking about tens of millions of authentication requests. So people are trying to sign into our products during those days, and we call them tax season. And impact of an 1 minute outage during the season is some thousands of transactions. So yes, in this context, resiliency do matter to us, and we have tried all these things that I'm going to talk about in production, and we have gracefully handled outages of dependencies. So this is the focus for today. So I have a microservice, let's call it A. And A calls another microservice over the network. Let's call that B. Hopefully, or perhaps over using REST or something else, that's fine. So this is simple enough, and I hope a lot of us can relate to this picture, especially if you are using microservices in production. So this is something that is very famous. This came from Werner Vogels, the CTO of Amazon. Indeed, failures are fact of life. At the same time, I also want us to know or be aware of the fact that the scenarios that I'm going to talk about, the resiliency scenarios, right, they are not the most common case. I mean, if we have built our system reasonably well, they're not going to fail 50% of the time, right? So it's very important that we have an availability goal in mind, and that's where it all starts. So this is really the beginning of beginning, right? So let's say my service gets 1 million requests in a day, right? Now, if I am achieving 99.9% availability, that means that I'm willing to tolerate 1,000 failures every day. Now, is it acceptable? It depends on the business, but that's really where it starts. Also, if I am trying to achieve 99.9% failure, and then if there are scenarios or faults that can happen maybe 1% of the time, 1% is rare, corner case, right? It's easy to say, hey, no, I don't care. I mean, it's really very rare. But if we ignore 1% cases, then we are actually not going to achieve 99.9, right? So that's something to keep in mind. So faults, what type of faults we can have? Back to the same picture that we started with. So we can have a network fault, or the dependency itself may be down, and the faults could be permanent, or they could be short-lived. It may not impact all the transactions, maybe some certain percentage of your requests fail, and so on, right? And this is our problem statement for the day. So as a person who wants to build a resilient microservice, how do I still deliver the best possible user experience given that the network is unreliable and the dependencies are also unreliable, right? So this is the outline of the talk. So I'll talk about 4 different patterns: bulkhead, timeouts, circuit breaker, and self-healing. And again, emphasis is going to be on the real life lessons that we have learned while using them in production, and not so much on the textbook. Okay, so the first one. So bulkhead. So the term bulkhead comes from the shipping industry. So like containers, for example. So a hull of a ship is typically divided into partitions, and those partitions are called bulkheads. And the idea is that if the hull breaches, it floods one partition, but doesn't breach the entire hull. So we'll see how to build on that. So let's look at this simple fragment of code. This is Java, but hopefully the syntax is familiar. I mean, it looks very similar to other languages as well. So I have two APIs. First one is called my health. So that does a shallow health check. It just returns OK. And this is used by the load balancer to just to know that this node is responsive, the web server, the Tomcat is responding, and that's it, right? And the second one makes a remote call over the network to a dependency, right? And what is it that is not right here, right? If we see this code little carefully, okay, so fine. So let's assume that we have done a reasonable job of designing our system. So the way we have provisioned our resources is like this. So say 99th percentile latency of the dependency API call, partner health, is 5 seconds, which means that 99% of the calls to dependency is going to finish in less than 5 seconds, but 1% can take more. And then the maximum TPS that we can expect to this API is 20, which means that we are talking about supporting 20 into 5, 100 concurrent requests, right? And then let's look at the shallow health, right? And since this is shallow, it just returns immediately. The 99th percentile latency is 0.5, and we need to support 10 TPS. So together we are talking about 10 into 0.5, that is 5 concurrent requests. So together we are supposed to support 105 concurrent requests, right? And then I give little bit of headroom. So let's say, okay, another 50% headroom. So let's say we should be able to support 150 concurrent requests. So I should have 150 threads in my web server, and we are good, right? I mean, reasonably well designed system. Now let's see what happens when the dependency is down. Meaning, this particular call, REST API call, is going to experience very, very high latency. What is very, very high latency? Average latency of 20 seconds. That's what we are talking about. And this is actually happened. This actually happened in system production. So I mean, I'm not making up these numbers. And let's say we have a TPS of 10. So that means that we should be able to support 20 into 10, that is 200 concurrent requests, and I just have 150 threads. In my reasonably well designed system, I only have 150 threads. I don't have enough threads. I'm going to see thread pool rejection, and calls are going to fail. Not only the calls to the dependency that are going to fail, but the shallow health, the my health API is also going to fail because they both share the same thread pool, right? And that's where bulkhead helps. Okay, now before that, so what really happens when the shallow health fails? So the load balancer is going to think that this particular node is unhealthy, the Tomcat is not responding, and it's going to take it out of the rotation. And if I have auto scaling, then a new instance will be launched, and that is going to have the exact same problem. So it's not going to help us, it's just going to be more confusing, right? Okay, so here is bulkhead. So the key idea is that I create a pool of threads for the making a call to the dependency, and that's a separate thread pool for the dependency, separate from the web server. So when there is a call to this dependency, when there is an API call from outside, partner health call, the web server thread pool asynchronously handovers the request to the dependency thread pool, right? And then a thread from that pool picks up the request and it makes a call to the dependency thread pool. But the thread in the web server pool is now free. Okay, so there is no way, I mean, how much ever time dependency is going to take, that's not going to impact the web server thread pool, and the shallow health check API is going to remain responsive. So I have been able to isolate the impact of my fault. I obviously cannot fix the dependency, but at least when the dependency is down, the impact is now limited to a certain thread pool and the certain API. The partner health API is down, my health is up, right? And you can generalize. I mean, you can have several APIs and several functions and so on. So this is what we have learned, that we could actually limit the impact of a fault and using bulkheading by creating pools of resources, and the resource could be threads, it could be connection pools, it could be so many other things, right? Now, what is still not good? So when the dependency is down, this API partner health is going to experience a very long latency, right? So which means that our users are going to wait, the callers of this API. So that is the problem, and that leads us to the next pattern, which is timeouts. Okay, so again some Java code using Spring framework, and the way you configure timeouts depends on the language and the library that you use. But typically most libraries support configuring two types of timeouts: the read timeout and the connection timeout, right? And this is what we call network timeout. So they apply when the dependency, there is a call being made to the dependency from the dependency thread pool, right? However, so this is the call that we are talking about, right? This is the call that we want to put a limit on, right? We want to ensure that this call always finishes within a certain time. And we have seen that we have configured two timeouts, the read and the connect timeout, right? Now, let's try to understand how much time this call takes and how we can ensure that this call finishes within my configured timeout, right? So let's slice the latency. So what happens first is that, if you recollect, we have a web server thread pool which hands over the request asynchronously to the dependency thread pool. And the dependency thread pool may be saturated, there may not be any free thread. In that case, the request has to wait in a queue, right? So that is the first part of this latency that we are trying to limit. Once a thread in the dependency pool picks up the request, first thing it does is that it makes a DNS resolution, maps the host name to an IP address, then establishes a TCP connection to that IP address, does an SSL handshake, and finally the data transfer begins, right? And the read timeout that I have configured applies only to the last phase, which is the data transfer phase. And then I also have a connect timeout, which applies to the this phase where we are establishing TCP connection. But again, this is actually k times connect timeout. What is k? So taking a step back. So typically, a host or a service may publish multiple IP addresses. For example, if the service is behind AWS Elastic Load Balancer, it does publish multiple IP addresses. And when a service advertises multiple IP addresses, a REST client tries to make connection to the first IP address. If that is unsuccessful, it tries to make connection to the second one, and so on, right? So it's actually, if a web service publishes k IP addresses, then there are k connection attempts, and this stage can take up to k times connect timeout, right? So the point here is this, that I have some configuration to control certain aspects of this overall latency, but not the complete thing. I have zero control over DNS resolution time, I have zero control over how much time the request waits in a queue, and so on. It's very, very difficult to guarantee the network timeout using this standard typical read and connect timeouts. And that leads us to the other type of timeout called application timeout. So application timeout is typically configured in addition to the network timeout, and it is driven by the business logic or the SLA that we have defined for our service. And so this is how you do it in Java, but I mean, different languages support it in different ways. To see it in picture, so network timeout applies when we are actually calling the dependency, and the application timeout applies between the web server thread pool and the dependency thread pool. So as soon as a web server thread hands over a request to the dependency thread, the time starts ticking, and if a response does not come back within the configured timeout, an error is returned to the caller. So that's how it works, right? So a quick example, so typically the network timeout, the way we configure is that it is like twice connect timeout plus the median of read latency. What that means is that I am allowing for 2 connection attempts to the service plus a read that should finish in median time, right? And if we define network timeout as that, and then you add some amount of headroom, and that could be a reasonable application layer timeout. Okay, so recap, so far with bulkhead, we learned that we can isolate the impact of a fault so that entire service is not down, just that a certain part of the service that has a dependency, hard dependency on that third party is affected. And we also know that we can put a hard upper limit on APIs or the latency of an API, right? So what is next? Okay, again, so we have an user which makes a call, API call, and that API times out. But what does the user do? I mean, what does it mean for the user, right? We just said, hey, sorry, we have timed out, there is a problem. Can we provide an alternative to the user quickly? And that leads us to the next pattern called circuit breaker. Okay, so again, same picture. So what we do with circuit breaker is a library which wraps all the calls to the dependency. Okay, and it is either open or closed. If it is closed, then it is allowing all the calls to the dependency to go through. If it is open, then it returns immediately without making a call to the dependency. And then we can have some logic where we can check if the circuit is open or closed. If it is open, then we can route the call to an alternative provider and provide an alternative, maybe a degraded experience to our user. So this is how a circuit breaker looks like. So it basically has three different components. There is a circuit, of course, which is either open or closed, and then there is a health sensor, so which tries to gather data about the dependency, how many calls were made in last 5 minutes, let's say, and how many of them were successful. It's a data collector. And then there is a finite state machine which uses that data and decides whether the circuit should remain closed or whether we should open the circuit, whether we should break, right? So that's how it is. And the benefits, as I already said, it helps us provide an alternative. And in some cases, there may not be an alternative. So in that case, what we can do is we can disable a feature which we already know that is going to fail anyway. And for the developers, it allows us to configure a fallback. And we of course don't want to overwhelm a dependency which is already under trouble, which is experiencing some issues. So, and what happens in that case is users typically tend to retry, and that kind of easily overwhelms that service which is anyway under duress, and we don't want to do that. So it is this is one way of achieving that. Hystrix. Hystrix is a Java library. It was originally developed by Netflix, and it was open sourced by them. Very easy to use, and it actually implements all the three patterns that we have discussed so far. Basically the bulkheads, the timeouts, and the circuit breakers, all three of them are implemented in this library. And as per Netflix documentation, so there are tens of billions of requests that are processed through Hystrix every day. So that's an amazing scale, and it's definitely a library which is battle hardened. But at the same time, as you will see, that it is really a piece of a puzzle. So our puzzle is the solution that we are trying to build, and this is one tool, but we have to ensure that the world solution works. And we really have to think about a few more things as and when we try to use Hystrix or a circuit breaker in general. All right, so Hystrix, again, simple Java code, and I just want to show you how easy it is. You just add an annotation in Spring, and you provide that fallback method, and that's it. I mean, you're on. So Hystrix, as I said, supports all the three patterns. So the first two configurations of Hystrix decide when to open or close a circuit. The second one is the application layer timeout, and the third one is helps us size or configure the dependency thread pool for bulkheading, right? So I'll not spend too much time on this. So let's see, now we have tried and spent some time playing with Hystrix, and what is it that we have learned. If your service is a cluster of nodes or cluster of servers, right, then Hystrix, there is a Hystrix instance in each one of them, okay, and they work independently. So there is absolutely no effort made by the Hystrix instance to talk to each other or coordinate with each other. So it's possible that the view of the data that one node has is slightly different from the view of the data the other node has, and as a result, two nodes will behave differently, or Hystrix in two nodes will behave differently. One of them will have the circuit closed, and other one will have it open. Right? It's normal; it happens. And one reason we see this happening is because a lot of load balancers, including Amazon ELB, work using a round robin algorithm. And when one node is fast, much faster than others, that node tends to get all the most of the traffic. And when a node opens the circuit, the latency of all the requests that go to that node, right, they all come back quickly, and their latency is really very small. So that node is the fastest node, and that tries to get most of the requests. Other nodes, which are actually calling a dependency and which is also, slow or down, they have a very, very high latency. So because of this asymmetric situation, the node with circuit open, which opens the circuit the first, gets bulk of the request. Other nodes starve, and they don't even have enough data to decide whether to open the circuit or not, right? So that type of leads to this type of inconsistency. What happens to the user? So let's say user makes a API call, and the load balancer sends it to one of the nodes. Let's say this is the healthy node, right? And it goes to the regular dependency, and user has one type of experience. And then the next call from the same user may land in a different node with the circuit open, and then that sends the call to an alternative provider, and user gets a different type of experience. So there is a possible that at user level there is a inconsistency, right? And how do we deal with that? So there are two ways to deal with, at least that's what I know. One is that we could use user session stickiness, so that all calls from a given user always goes to the same node. But that also has its own set of problems, like what happens if that node is out of service and all that. But nevertheless, this is not what we have used, by the way. We ended up doing the second one, which is creating a circuit breaker, which is more centralized, which looks at the data from all the nodes and decides. And we'll talk a little more about it when we talk about self-heal. But just to give you an idea of where we are headed. Okay. So as with any technique, right? So I think we should really, when we use that in a system in production, it is super important that we know what are the metrics that are important for us to know that this is actually working for us. For circuit breaker, the parameters or the metrics that we look at are the response times. So let's say a dependency goes down at time t and the circuit opens at time t1, right? So t1 minus t is the delta, right? That is the response time for us to break, right? And since we have delayed it, like we have not been, it's not a perfect system, right? Since we have delayed it, so there has been some amount of user impact, right? So that is the user impact because we could not open the circuit soon enough. That is one metric to track. The other one to track is that once the dependency recovers, right? Again, the circuit breaker has to figure out that, oh, this has recovered, now I can close. And since we did not close it soon enough, again, we presented user with a degraded experience for some time. So that is the other metric, the user impact, since we did not close the circuit soon enough, right? So these are the two key metrics that we track for circuit breaker, and we'll see how those metrics actually lead us to the additional interesting scenarios. So we are talking about end-to-end behaviors here. So I have service A, which calls another service B via a circuit breaker. B calls C again via a circuit breaker, right? And it's possible in a company, a big company, right, that these two services are owned by different teams. Their historics is tuned differently, right? And it's possible that the historics or the circuit breaker in B is more sensitive to failures than A. So when C, the final dependency goes down, B detects it fast and decides to open the circuit. However, A is still waiting for more data. For example, B may decide that, okay, if I see 10 requests and say 8 of them fail, I'll open. A, on the other hand, may be configured so that it gets to see 100 requests and then 80 of them should fail and then it moves. So this type of things are possible, right? Now, what happens in this scenario? So other thing is that A has an alternative experience. So when the A circuit of A is open, it forwards the request to the alternative provider, but B doesn't have an alternative, right? Now, in this case, the errors that B throws actually propagate all the way up to the user. That's not what we want actually. What we ideally wanted is to users to see the alternative experience, right? But that's not what is happening, right? So the second one is, so basically this is really the problem of us not opening the circuit soon enough. The circuit in A did not open soon enough, and as a result, user got impacted. Users are actually seeing errors instead of the alternative. Closing the circuit, right? The circuit breaker, as I explained, right, needs data to decide the health of the dependency, right? And if there is no data, then it cannot make a decision and it remains where it is. So again, the same picture, but in this case, we have both the circuits open, right, A and B, and all the calls that land in A go to the alternative provider, and B gets no calls at all. Now, let's say C recovers at some point. How will B ever know that C has recovered? Because it's not getting any traffic, it's not able to, it's not getting any data at all about the health of service C. So, I think the key is that we understand those metrics that matters to us, and we do an end-to-end testing. It's not enough to test my microservice, but also the entire system, especially with this type of patterns in place. And in this specific case, we could also use a synthetic traffic generator. Again, something I'll touch upon when I talk about self-healing. Okay. So the next one is about request volume versus error volume. So Hystrix configuration has basically decides Hystrix decides to open a circuit based on two configuration parameters: request volume threshold, the first one. The request volume threshold and the error threshold percentage. So with examples, so request volume threshold could be 100, which means that in a window like 5 minutes, there should be at least 100 requests before Hystrix decides to open the circuit. And error percentage threshold is 50, which means that error percentage should be greater than 50% so that Hystrix opens the circuit. Right? So let's look at this scenario where in a window, I have 5 requests and 3 of them failed, which means that my error percentage is 60%. But intuitively, do I really want to open circuit? Do I know enough about the dependency to say that it is down or unhealthy? No, because it could be just some random errors as well, just 3 random failures, right? And we don't want to open and close circuit too often and confuse everybody, right? And indeed, since I have only 5 requests and my threshold is 100, a circuit does not open. This is highly desirable. That is really the whole idea behind having a threshold, 2 thresholds. One is on percentage, second one is on volume. But let's take this scenario, the other scenario, where I have 50 requests and all 50 of them has failed, right? All of them has failed, which is 100% error rate. So this is very, very drastic scenario. And intuitively, at this point, I actually know that my dependency is unhealthy, right? If I look at this data, I will probably bet my money on saying that, yes, indeed, the dependency is down. But what happens in this case is that since my threshold is on request volume and I am expecting 100 requests, right, I'm not going to open the circuit. And this is not exactly what I desire. We are not failing fast enough, right? So if you think about the 2 metrics that we had, the 2 response times, here we are not closing the circuit soon enough. And as a result, we are actually impacting our users by not doing that. So the intuition is this, that when the error rate is very high, we actually need a smaller sample to be confident that the dependency is unhealthy, right? Like when it is 100%, I actually do not need to see 100 requests. I can take that decision even at a smaller sample size, right? So that's why the idea is that instead of thresholding on the request volume, maybe we should threshold on the error volume. And that also has a nice sub-property that we have a direct control over the user impact, the number of users we are going to impact before we decide to act. Okay, so let's take 2 sample configurations and do a quick A/B test here. So the first configuration is the traditional Hystrix one, where we have request volume threshold of 100 and error threshold is 50. Second one, config B, uses error volume threshold of 50 and error threshold is exactly same, which is 50%. And then let's do a quick simulation. So here the scenario is that my error rate is 50%, right? So 50% of all my requests are going to fail. And as you can see, right, that both the strategies work exactly the same way. Right, so I have to see 100 requests and 50 of them should fail, and then both the strategies decide at the same time that it's time to break. Now let's look at the more drastic scenario where my failure rate is 100%. All calls that are going to the dependency are timing out or failing. Here, The request volume threshold unfortunately still needs to see 100 requests because that is my threshold. But error volume threshold reacts much faster, right? It sees 50 requests, all of them fail, and it breaks the circuit. So we fail faster. So, so unfortunately, Hystrix does not implement error volume threshold. There is a Jira, rather an issue in Hystrix GitHub issue tracker. So at some point, I hope this will be implemented. But till then, I think we can create a pull request, or rather, we can create our own fork and implement that, or use our own circuit breaker. So to recap, we learned 3 patterns: bulkhead, which allows us to isolate the impact of a failure, and then we know how to put a hard timeout, and also we know that with circuit breaker we can provide an alternative. So what is next? The next one is about so self-healing, right? So the dependency has recovered, and how do we know that we have to recover now, right? And here I introduce this term called management plane. Management plane is actually not a new idea as such, but just that this term is not used often and the idea is not studied or talked about a lot. But let me quickly introduce that. So by data plane, I mean the actual service where or rather all the subsystems of the service that implement all my functional requirements, right? So service A calls service B, there are users, all this is data plane. And then if I run this service in production, I will have a monitoring system, I will have alarms configured, and then there will be an on-call engineer taking those alarms and taking some corrective actions in response to that. So whatever else that we have in my service that is required to operate or test my service are they form the part of what is called management plane, right? As I said, it is not a new idea. For example, Kubernetes has a similar concept. And also, I think yesterday I was in the Avi Networks booth, and they also have a controller, which is really the management plane, which decides, whether to scale out and so on, right? So basically, we have nicely separated the functional requirements and the operational requirements into different sets of subsystems. And also, if you see, we don't have that on-call engineer anymore. We have a bunch of scripts or programs. And they trigger when the alerts fire, and they automatically take the corrective actions. And then we have, and human of course, now this human is a DevOps engineer who is actually writing those programs. So this is how it is, in an ideal management plane, this is how it looks like, right? And so corrective actions is where the meat is. So those could be REST API calls back to the data plane, or those could be simple SSH, so you do a remote command execution using SSH, right? And what is it that we can do here using the management plane? We could implement our circuit breaker, which really looks at the cluster level data and decides. We could also have a synthetic traffic generator to decide whether the dependency has recovered. We could also use the management plane to reload some data, or SSH to the each node and restart some process like Tomcat, right? So these are my corrective actions. So let's see how we implement a circuit breaker using this. So just to recap, circuit breaker has 3 main components: the actual circuit, a sensor, and the finite state machine, the decision making component, right? And here this is how it looks like with management plane. So the service, the nodes of the service still has the sensor and the circuit, but the decision maker, the FSM, is now in the management plane, right? So this is where it is. So this is where the decision making is happening. So all the data that flows from here goes to the monitoring system as before, and then when certain thresholds breach, that causes an alarm, and the alarm triggers this finite state machine, and then based on the data, it decides to open or close the circuit. And then there are REST API available here, which allows this component to open or close circuit from outside. And then we could also use this to implement synthetic traffic generator. So when FSM decides to open the circuit, it also triggers the traffic generator. This is another program here, and which pumps in the synthetic traffic from time to time to decide whether the dependency, the service B, has recovered. So even though it is intuitive, it is also there are certain pitfalls and there are certain key considerations that we have to keep in mind to ensure that this actually works. So one of them is that we should start with operability in mind. When you are designing my service or system, operability is one of my requirements, right? Which means that the service itself should define a bunch of REST APIs to simplify the operational tasks like open or close circuit. And it is very, very desirable that those APIs are idempotent so that if they fail, let's say management plane, one component in the management plane makes a call, calls that API and it fails, it is perfectly safe to retry, right? I can give quick examples like, so we can define an API to open a circuit and no matter how many times you call that, circuit is going to open, that is the end result, same. So this is good. Bad would be defining an API which will toggle the state of a circuit, because that depends on the current state of the circuit. If current state is closed, you call toggle, it opens, call toggle again, it closes, right? Outcome is different depending on how many times you call it, not good. Okay, the other one is the dependency flow. The whole management plane is also new code and there is a network involved. The new code may have bugs and network may go down, there may be GC pauses, there may be transient network issues like congestion and so on, right? Now what happens if any of this happens, right? Does it impact the overall availability numbers of my service? It should not, right? So the data plane should not depend on the management plane, but it should be the other way around. So management plane should depend on the data plane, right? So again, another quick, easy pitfall. So let's say I design my service so that when a node in data plane comes up, it makes a call to the one node in the management plane and tries to get some data, right? Let's say some configuration or some data that it needs, right? Now, what if while this node is booting, the network is broken, right? It cannot make that call. It fails. It cannot boot, right? That's really a bad place to be in, right? The better way to do it would be that the node comes up with some default values, maybe the last known value, and then there is a refresh call that is made from the management plane to the data plane to fetch the latest version of the data. Okay. So to summarize, so these are the 4 patterns that we talked about, and bulkhead for fault isolation, timeouts, a circuit breaker to provide alternative, and separate management plane for self-healing, and also other possible operational requirements. So dependencies do fail. I mean, all of us who have actually worked in production and have been operating systems know that. And there are techniques that help us, but the key thing is that with every technique, they are just really a piece of the overall puzzle, right? So we have to understand end-to-end behavior. We should know what to look for, what are our metrics to look for. And lastly, so awareness, observation, and refine. So these are the really 3 key phases that through which we go through in our journey. So I call this meta learning. So these are the learnings that help me learn. So the journey that we have been through may not be exactly same as the journey that you will go through, and your lessons may also be different, but it is important that you learn. And in order to learn, these are the principles that help us learn, right? If I am using a technique or some pattern or some library in my system, then I should understand that what are the key metrics to track, and also define the target SLA for each one of them. So if I have a database which replicates between 2 data centers, then perhaps replication lag is one metric to keep in mind. If I call another API over the network, then maybe the latency of that call. If I am using a circuit breaker, then maybe the response times that I talked about, right? And then once we deploy my system in production or in test setup, we use the data. We actually gather data. We see what are the actual values. And if they deviate from the target, we come back here and we refine. So this is what I will leave you all with. And hopefully this is helpful. Thank you. Happy to take questions if you have any.
Yeah, we have 5 minutes of time. Any questions? Please raise your hands. Okay. There don't seem to be any questions, or the audience is too shy.
Okay, I think.
Yeah, we have one question here.
From production side, I have a question on the load balancer and from your experience, because you're also dealing with high volume transactions. What would be the situation where you have two load balancers and you would not keep them in hot and you would keep them only in hot-cold? Could you think of some scenarios where that would be the right configuration instead of having it in hot? Okay.
Yeah, so so I think there are different load balancer architectures. I think the one that is popular these days is where you neither have hot. It's really like you have a distributed set of nodes doing load balancing, and if one of them goes down, then automatically the other one replaces it, and so on. If you really want to have a hot, cold, I don't know why you will actually design your load balancer that way. I mean, then you also have to worry about the time it takes for a system to decide that, okay, this load balancer is unhealthy and let's do a switchover. So there is a failover time, right? And during that time, you are impacting your users, right? Because you are still sending traffic to the unhealthy node, which cannot forward requests anyway, right? So I think nowadays, like for example, if I look at ELB, it's not like it is completely distributed. There are multiple nodes, and DNS does some magic. So DNS always returns the IP addresses of different nodes at different calls. So that way the load balancing, I mean so DNS sends requests to different nodes and then they forward to the other nodes. So that's how the whole thing works.
Okay, back there.
Hello. The thresholds you mentioned, are they dynamic or you go and tune them? If you tune them, like how do you make the services aware of it? So does it need a manual intervention? How do you manage that?
You're talking about the circuit breaker thresholds?
Yeah, what are the thresholds, what you have configured? Are they like static throughout, or but I think it should be dynamic so that you kind of be resilient.
And why do you think those should be dynamic? Because that's not what it is, by the way. This is like configuration.
Okay.
So those are configured, and then when the service comes up, they don't change. Okay.
Okay, you never come up with a situation where you need to go change or anything like that.
Yeah. So typically we, yeah. So there are people. So there is a way to externalize configuration, right? You could actually have a configuration service where you maintain the configuration and change it on the fly, right? That could be one way. But then, how do you test it, right? You made the change in production, and you don't know if that's going to work, right? So I think the more conservative approach is to actually make the change and go through the regular testing CI/CD and then deploy it, so that you know that whatever config change is coming has already been through the same set of testing that you do usually. Yes, but depends on what type of configuration it is. Like, let's say you have something really safe, like you want to disable a feature, right? That probably is safe, and you can probably use a feature flag to disable it on the fly. But if it is something more complex, like tuning the circuit breaker, it typically takes time, right? Because you really want to be sure that your parameters, the metrics that I talked about, the time to close and time to open, right? They are really within the our SLA limits. So usually we don't do it on the fly.
One question this side.
So you talked about despite of doing all these things, dependency can still fail. So are you also recommending alternative design also? Like in some cases where it happens that there is a synchronous call is needed to complete that transaction, but still can we segregate it and think of a scenario where if it is off, still my system is on and maybe I can do a later processing. So are you also working on that? I mean, do you recommend?
Yeah. So we have synchronous services. We also use asynchronous services where we have a JMS-based queue, right? So the caller really gets a request, puts it in that queue, and then there is a consumer which takes it up and calls the dependency. But the consumer is still synchronous. So everything that I talked about still apply here. But from the end-to-end point of view, so I have quickly responded to my caller, caller of my service, saying that, okay, I will do it later. It's not 200, it's 202. Accepted. I'm going to work on it later, right? and then I can do retries and so on, right? And actually, sorry, I just remembered, so as I mentioned retries, so with retries, I think when the dependency goes down and then we do retry, right? Again, retry is a big topic in itself, but we have to be a little careful to avoid this thundering herd problem, where, you know, lots of retries suddenly, you know, pile up and, you know, again brings that service down. So it could be just a flip-flop, right? It goes up and then again comes down because of this huge surge of retries.